Welcome back, everybody. Um, we're solving problem 23.79 from the textbook University Physics by Young and Freedman. We've done solving parts A and B, so if you have not seen them, I urge you to see them right now, because it'll be difficult to follow what's happening here in parts C and D. Alright, so what we have to do in part C and D is pretty simple. Here's a little a quick diagram of what we did. Wow. Okay, so we have a rod, and we have points R and P, and we have to find the potential at P and R when they're at a distance of x and y respectively. This was parts A and B. These were parts A and B, and here in part C what we're doing is to find what the potential at P would be if x is a really large number. Alright, and the same with D, where we increase y to a large number. All right, let's see what happens there. So this is what we found in part A to be the potential at point P. All right, so let's call this 1 over 4 pi epsilon naught k so that we can save some time writing. Vp equals k q over a times natural log of, look how I'm going to split this thing now, x over x plus a over x. Okay, so kq over a natural log of 1 plus a over x. Now if you refer to the appendix B of the textbook, I think there is a expansion to this term, this very term. Alright, natural log of 1 plus a over x can be written as, in fact, you know what, let's call this u for now so that it's simple to understand. It can be written as u minus u squared over 2. Okay, the expansion continues there. So instead of u, all we have to do now is just replace it with a over x. Okay, so what will happen here? A over x minus a squared over 2x squared. This is natural log of 1 plus a over x. Okay, so now here we want to see what happens when x increases to a large number. So if x increases to a large number, here x squared would be a super large number. And if you have a very big number in the denominator, the entire term is going to be really small, so it can be neglected. Okay, neglect. So we consider this to be only a over x. Substituting that there, kq over a times a over x. Okay, so a cancels, so you have kq over x, which is proportional to 1 over 4 pi epsilon naught q over x, which is what? Which is the same as the potential at a point due to a point charge. Remember, we discussed the first thing in part A was this, right? This is where we start from. So if your x is a really large number, by approximation of the natural log thing, that you come back to the same thing, you know. It's kind of intuitively, if you see, if you're having a very large distance, the rod is as good as a point charge, right, with charge q, and the distance between them is just x. All right, so try to relate it to the point charge potential, and I think it'll be very clear. All right, now that we've done this part, let's go to part D. All right, so this is the answer of part C. So let's go to part D. I've written the question down here. Here it is. Okay. Oh wow, I think I missed a few terms here. Okay, it's a squared over y. This is the answer we got from part B. So answer from. But this is part D we're solving. So again, let's call this k q over a, and again here let's split this up to a over y plus root of y squared plus a squared over y, and let's play with this term right here. Okay, y squared plus a squared over y can be written as the whole root of y squared plus a squared over y squared, right? Just taking it inside the root there. And then here, split the denominator. Split the numerator. Y squared over y squared plus a squared over y squared, which will give you what? Root of 1 plus a squared over y squared. Is that very clear? Alright. Now from here, again, going back to your appendix B of the textbook, there's an expansion for this as well. So, root of 1 plus a squared plus y squared. How many people don't like this color? Like, I can't see how many people don't like, but I just don't seem to like it. I mean, not that it's a bad color, it's just that it's not picking up here. Alright, let's expand this to 1 plus a squared over y squared, the whole power half, right? That's what the square root is all about. And there's an expansion to this. And it is 1 plus a squared over 2y squared. Okay? This can be seen from the appendix B of the textbook, so don't worry. So this is what we can write as for the expansion of this part here. Okay? A squared over 2y squared. Now you also have another term in the main equation, a over y, right? So if you do a over y plus root of 1 plus a squared over y squared, you're going to get 1 plus a over y plus a squared over 2y squared, right? A squared over 2y squared is from the top here and 1 is from there, but a over y is from the main equation. So finally, if you see, and again here, as in part C, x is growing large in part C, and in part D, y is growing large. And if y is growing really large, y squared again is super large, and we can neglect it. Okay? So all you're left with here is 1 plus a over y as an approximation, which is fair enough, okay? Because y is really increasing large. Now, if you go back to the equation that we have for potential at r, you're going to get kq over a natural log of, the approximation of this is going to be this, right? So 1 plus a over y. This is not 9, this is a. I'm very bad at handwriting. Okay, very bad at good handwriting. Alright, now from part C we expanded this, right? 1 natural log of 1 plus u, and here it's just 1 plus a over y, which can be written as what? To jog your memory, natural log of 1 plus u equals u minus u squared over 2. So 1 plus a over y would equal a over y minus a squared over 2y squared. Again, y squared is super huge, so we're neglecting it. We just take a over y. Substituting that here, what do you get? VR equals kq over a times a over y. And a cancel. All you're left with is kq over y. Again, if you expand k, it's 1 over 4 pi epsilon naught times y. And here you have a q, which is the potential at r if y goes to a really large number, which is similar to what we derived in part C, right? And again, as y increases, the potential at r is equivalent to the rod being a point charge of charge q. Alright? I hope this was clear. If it's not, just rewind and watch again. That's the best part of YouTube. You can watch it how many ever times you like. Great. It was great solving this problem with you guys, and hope you enjoyed it as well. Alright, see you soon. Bye-bye.